In this video, we are going to examine using the second derivative test to identify local extrema on an original function. In my class, have already used the first derivative test to identify local extrema, but now we're going to look at how you can also use the second derivative to identify local extrema. But first, if you are in my class, I'd like for you to stop the video, complete this warm-up, and then resume the video and check your work to see how you did. If you're not in my class, you may want to skip ahead to the second derivative test to see how that works. So what we have here, the instructions are to draw a possible graph that indicates that perhaps there's more than one way to accomplish this. We're graphing a function whose name is f of x, and the function that we're drawing must satisfy the following conditions. So what you can see is that we have 5 conditions, 5 attributes that we're going to use to describe or to draw a graph of a possible original function that would meet all the criteria. When you are reading and investigating the various pieces of information, I would encourage you to look at the pieces of information by type of information. For example, in number 1, we see that the information that's being provided is given about the first derivative, and in number 2, the information that's being provided is given about the first derivative. So I would personally take that information and transfer the information onto a first derivative number line. We can see that the first derivative is positive when x is greater than -1, and the first derivative is negative when x is less than -1. So it appears that -1 is a critical number, at least that's what I'm gathering so far. To the right of -1, the first derivative is positive, indicating an increasing interval on the original function, which is what I'm trying to make a graph of. And the first derivative to the left of -1 is negative, indicating a decreasing interval on the original function. So I've taken that information out of symbols and into a number line. The next pieces of information deal with the second derivative. So both statements 3 and statements 4 are information regarding the second derivative. So I'm going to take that information and transfer the given information onto a second derivative number line. The second derivative is positive when x is greater than 2. So I'm going to put the number 2 on my second derivative number line, and that tells me that the original function in that region is concave up. The second derivative is negative to the left of -1, so concave down, and between -1 and 2. So the function stays concave down, and -1 is not a point of inflection. But 2 appears to be a point of inflection because the second derivative changes sign at x equal to 2. Now the last piece of information is statement 5. That tells me that the limit as x approaches -1 of the original function is -infinity. So let's start building a graph. So at -1, on that graph, from both sides, the function or the original function f of x is approaching a y value of -infinity, which leads me to believe that I have a vertical asymptote at x equal to -1. Therefore, -1, although it appears like it's going to be a local minimum based on my first derivative number line, remember a critical number is where the first derivative is 0 or undefined. So I'm going to make a vertical asymptote to take care of statement number 5. Now looking at -1 on my number line, to the left of -1, there are two things that are happening. The original function is decreasing and the original function is concave down. So I'm going to draw a graph that's decreasing, concave down, and approaching the vertical asymptote. So my graph could look something like that. At x equal to 2, I've established that I have a point of inflection. To the left of 2, the graph is concave down, and to the right of 2, the graph is concave up. But at the same time, I'm supposed to have a function that is increasing. So there's 1, there's 2. So my graph is going to approach the vertical asymptote or come from the vertical asymptote, travel to 2, and then my concavity needs to change so the function flattens out and continues to increase. So you can see that I have a concave down interval from -1 to 2 and a concave up interval from 2 to infinity. So if you want to see that, there's my concave down interval, there's my concave up interval. So I have met all 5 criteria, and this is a possible graph of an original function that meets all of that information. Let's move on now to the second derivative test. So what you see are 3 graphs in front of you. The first graph is f of x, which I will call the original function. The blue graph is the first derivative graph of the original function, and the red graph is the second derivative graph of the original function. So let's see what we're going to do here. Number 1, we're going to identify the relative extrema of the original function. So since we have the original function here, we can clearly see that there is a, let's do that in red, there is a local max at x equal to -1, and I intentionally gave you a graph where you can identify these values easily. And there is a local minimum at x equal to 1. Local max at x equal to -1, local minimum at x equal to 1. So let's write that down. Local max at x equal to -1. And the local maximum, well, let's go ahead and say and is f of -1. Because remember, the y value is actually the maximum value. Whoops, too far. Let's slide that back up. There we go. Sorry about that. There is a local minimum at x equal to +1, and that local minimum value is a y value of f of 1. It's the function when you input 1, you output the y value. So we have identified the local or the relative extrema of the original function. Remember, the word relative and local are interchangeable. Secondly, we're going to use the first derivative to justify our conclusions from number 1. All right, so let's go back. This is really an application graphically of the first derivative test. So if we go over to the first derivative, we see that we have a critical number at x equal to -1 and a critical number at x equal to +1 because the first derivative is 0 at each of those values. We also see that let me get a highlighter here, we see that the first derivative is positive to the left of -1, and that the first derivative, let's change colors here, the first derivative is, oops, I did not change colors. The first derivative is negative to the right of -1. Therefore, by the first derivative test, there is a local maximum that occurs at x equal to -1. And then we can see the first derivative graph goes positive again. Oh, come on. First derivative graph goes positive again after x equal to 1. So there's a graphic representation of the first derivative test. So we wanted to justify using the first derivative test. So let me write that up. So the justification, there's a local maximum at x equal to -1, and it is f of -1 because f prime, the first derivative at -1 is 0. That establishes my critical number. And the first derivative changes from, and then you go back up and you read your graph, the first derivative changes from positive to negative. And then similarly, there is a local minimum at x equal to 1 and is f of 1 because, so using the first derivative at 1 is 0, establishing a critical number, and the first derivative changes from negative to positive. So I have used my first derivative test to support and justify my local or relative extrema at those particular values of x. So that's done. Number 3, use the first derivative to identify any critical numbers for the original function. We already did that on the graph above. Recall that we said that there was a critical number at x equal to -1 and x equal to +1, and the justification is because, in this case, the first derivative is equal to 0 at those values. So that just supports what we already wrote up in number 2. So note that 1, 2, and 3 is simply a review of how to use the first derivative test to indicate local extrema on the original function. Now we're going to ignore the first derivative for just a few minutes, and we're going to take a look at the second derivative. So let's see what number 4 says. Number 4 says, determine the sign, positive or negative, of the second derivative. So we're looking at the second derivative at each critical number. So let's go back up here. The critical numbers that had been identified on the first derivative, we have a critical number at x equal to -1. Whoops, critical number. And we have a critical number at x equal to +1. So let's go over to the second derivative graph. And at x equal to -1, on the second derivative graph, notice that the second derivative at -1 is less than 0, or the second derivative is negative. And similarly, if you take a look at the other critical number, we said the other critical number is at x equal to +1. If you go to +1 on your second derivative graph, you'll notice that the second derivative at that critical number is greater than 0. Now, let's make a connection. Notice that when we had a local minimum on the original function, that the output of the second derivative is greater than 0. When we had a local maximum on the original function, we identified the critical number using the first derivative, but the output of the second derivative is a negative number. And that's kind of one case of demonstrating how the second derivative test works. So let's take a look and summarize what we're trying to say here. And again, this is one case, but I'm showing generally what is actually true using the second derivative test. So the first thing we want to note is that the second derivative test, what is it used for? Well, the second derivative test is another method in which we can identify local or relative extrema. What does the second derivative test say, or how do you use it? Well, the second derivative test says our conditional statement if, let me grab a pen here, if C is a critical number. So clearly, just like always, when we're trying to locate local or relative extrema, we first have to identify the critical number. And to identify critical numbers is where the first derivative is 0 or undefined. So just like before, we must establish a critical number. Once we get that critical number, we can take the critical number and substitute it into the second derivative. If the output of the second derivative is greater than 0, and you can look at the graph that we just looked at to verify this. Oh, I didn't have the then. I'm going to write that up. Let me write it up for you. I thought it was under the slider there. So if we have a critical number and we substitute that critical number into the second derivative and we get a positive number, then there is a local minimum. You would want to think that there's a local maximum because the output is positive, but there's a local minimum on the original function f of x at x equal to c. Second derivative test. Then, if we establish a critical number and we take that critical number and substitute it into the second derivative, edit, undo, and we substitute that critical number into the second derivative, if we get a negative, then there is a local maximum on f of x, so everything goes back to the original function, at x equal to c. And then the last case is if you have a critical number and you substitute that critical number into the second derivative and you get 0, then nothing can be determined using the second derivative test. Now, a logical question that would arise would be, well, if we have to go through the first derivative to get to the second derivative, to use the second derivative test, and we have to use the first derivative to get critical numbers anyway, why wouldn't we just use the first derivative from the get-go and not worry about the second derivative? And I'll show you, I'll demonstrate a case and a time where you would actually need to know the second derivative test. So let's take a look at how to use it. We have the first example. We've been given a fourth degree or a polynomial function. I've already calculated or found the first derivative for you. So here's the first derivative. And here we have the second derivative already done for you to save a little bit of time. We are looking for any critical numbers for the original function. So critical numbers come from the first derivative being set equal to 0 in this case, because we know that a polynomial has nowhere where the first derivative is undefined. So we're going to set the first derivative equal to 0. I'm going to factor out a 4x squared, so that'll give me an x minus, factoring out a 4 would be 3. And so we get critical numbers of x equal to 0 and x equal to 3. That's for phase number 1. Identify your critical numbers just like always. Now we're going to use the second derivative, not the first derivative, to determine any local extrema. So we do not have to make a number line when we're using the second derivative test. Second derivative test says we're going to take those critical numbers and substitute them into the second derivative. So the second derivative evaluated at 0 for this particular function is 0, so we cannot determine whether or not there is a local max or a local min using the second derivative test. Let's just see what happens at 3. So when we substitute 3 into the function, 3 squared is 9, 9 times 12 minus 24 times 3, so that would be 12 times 9 minus 24 times 3, so 9 times 2, 72, which is greater than 0. So now I know that there is a local minimum, because the output was greater than 0, a local minimum occurs at x equal to 3 and is f of 3 because f prime of 3 is 0, establish the critical number, and the second derivative at 3 is greater than 0. So in that case, honestly, I could have stopped at the first derivative. I could have made a number line. I could have put the critical numbers on the number line. And I think I will actually come back to that in just a second. So the question in the question has not been answered yet is, why would I actually need to know the second derivative? Well, hopefully our second example will illustrate that for you. Notice in the second example, you have already been given that the first derivative of a mysterious function that we do not know is equal to 0 at -3. So that establishes that there is a critical number at x equal to -3 on f of x, the original function. So I have established my critical number, and I have the second derivative. I don't even have the first derivative, and I don't have the original function. But according to the second derivative test, if I have a critical number, I can substitute negative 3 into the second derivative. And so that's going to give me negative 2e. I believe that's pi x. Let's see if I can make that big enough to actually read it. I think on your paper it's probably more evident or more clear to see. I'm going to go with that this is negative 2e pi x. So if I substitute negative 3, okay, and remember, all I care about is whether the outcome of the second derivative is positive or negative. So that'll be negative 2 divided by e to the 3 pi. So in the numerator, I have a negative number. In the denominator, e to a power is going to be positive. So that's going to output a negative. Therefore, I would say a local max occurs at x equal to negative 3 and is f of negative 3 because first derivative at negative 3 is 0 and second derivative at negative 3 is less than 0. So a local maximum. All right, so using second derivatives is pretty easy. All you need to do is determine whether the outcome is positive or negative. 0 can create a little bit of a problem. So let's go back up to the first problem. Trying to figure out where I want to do this here. So I think what I'm going to do is to erase my work in number 2, because you can go back and look at that or stop the video and copy down whatever it is you need from that. And I want to apply the first derivative test to the example in number 1. I'm going to slide this out of my way for right now to make room for the work that I want to continue in the first example. So if we were to ignore the second derivative test and just continue, let's kind of mark that off like that. We've established the critical numbers of the original function using the first derivative. I'm going to take those critical numbers and put them on my first derivative number line, 0, 3, and let's see what we find out now. I'm going to substitute a negative 1 into the first derivative. So when I substitute negative 1 here, I get a positive. When I substitute negative 1 into this factor, I get a negative. And a positive times a negative is a negative. Therefore, the original function is decreasing on that interval. When I choose a number between 0 and 3, such as positive 1, if I substitute into the first factor, I get a positive. Into the second factor, I get a negative. A positive times a negative is a negative. Therefore, the original function decreases, so there's not a local anything going on there. And then I'm going to substitute the number 4, which into the first factor gives me positive, second factor gives me positive, a positive times a positive is a positive, so the original function increases, so we can see that there is a relative or a local minimum confirmed occurring at x equal to 3, and we found the same thing using the second derivative test. Now, if you're in my class, you can turn in your packet to page 21 and see a summary of the second derivative test, or I'm sorry, to page 22, unless I've updated the packet and the page numbers changed, but you'll find that summary. On page 23 in your packet, you will find what I call the All About Me sheet. The beauty of this sheet is that it summarizes everything we've been talking about regarding the first derivative test, the second derivative test, the concavity. So I would very much encourage you to take a look at page 23. You'll notice that my page 23 looks a little different than yours. This is the colorized version, which I'm going to post in the Google Classroom, so you can also print your own colorized version and use this as a study guide. So anyway, I hope you were able to use this to help you with the second derivative test.